So this morning's briefings are from Soren Meibom, who's going to be talking about the Kepler cluster study toward the ages of stars and their planets. He'll be followed by Courtney Dressing, who will be talking about a recipe for Earth-like planets. And she'll be followed by Laura Schaefer, talking about the persistence of oceans on Earth-like planets. And then our commentary will be provided by Deborah Fisher of Yale, who has been in this business as long as anybody and will give us some perspective on where today's results fit into the bigger picture. And with that, I will turn it over to Soren, and I will even try to bring up Soren's presentation before I sit down.
Thank you, Rick. Good morning. As you know, NASA's Kepler mission has been tremendously successful in helping us understand the frequency and the diversity of planets and planetary systems beyond our own. Today, I will tell you about the latest results from the Kepler cluster study. As part of the original Kepler mission, a main goal of the Kepler cluster study was to build a clock for the stars. That is to say, to make measurements with Kepler to help us develop a method to determine the precise ages of cool stars. So what are cool stars? And why is it important to know their ages? A cool star is a star similar to our sun, or smaller. They're most numerous throughout the solar neighborhood and the galaxy. And they also live very long lives, so they act as lampposts, lighting up even the oldest parts of our galaxy. So numerous and luminous, young and old, astronomers use cool stars to study the universe from its early days till recent times. So now I have told you about the value of cool stars. Why do we want to know their ages? Well, just as organisms here on Earth change and evolve with time, so do stars and planets. And to understand this evolution, we need to establish a sequence of events. Here on Earth, for example, in order for us to understand the evolution of our own species over millions of years, we had to develop methods to date the fossil bones of our ancestors. But in space, the formation and evolution of stars and planets, clusters of stars and galaxies, takes place over hundreds of millions of years, even billions of years. And knowing the ages of the stars that make up these systems is as important to our understanding of astronomical phenomena as it has been to us to understand the human evolution, to know to be able to date the bones of our ancestors. So now you know why it's important to know their ages. So the next thing I'm going to tell you is determining the age of a cool star is a very difficult task. And the reason is this. As this diagram illustrates, the mass and the size of a cool star remains almost constant throughout its life, as well as its most easily observable properties, such as brightness and temperature. And to drive this point home, I usually ask you to imagine for a moment that the same was true for human beings. Let's imagine that we were born as small babies, but by our first birthday, we looked like an adult. And we stayed looking the same through our 20s and 40s and 60s, even 80s, until we suddenly appear old. If that was true for humans, we wouldn't be able to look at each other and tell each other's ages. We would have to find something else about us that would change steadily and visibly as we grow older. And that is our challenge for cool stars. To find something about cool stars that change steadily with time and that we can observe. Luckily, there is one such property for a cool star. Its spin rate. A cool star's spin is very fast when it's young, but just like a top on a table, it gets slower and slower as the star grows older. So we can use the spin rate of a cool star as a clock, and we refer to this method as gyrochronology. So the idea of this clock is really simple. We want to make measurements of the spin rates of cool stars for which we already know the ages. And we want to then establish a relationship between spin and age for cool stars in general. Because if we can do that, then we can take any cool star in the sky and measure its spin period and use this relationship to determine its age. Now, why do we need NASA's Kepler mission to do this seemingly simple task? Let me answer that by showing you how much of this clock we had built before Kepler and the Kepler cluster study. We knew spins and ages for cool stars younger than about 600 million years. And you may ask me, how come we knew the ages of those stars? And this is where the word cluster in the Kepler cluster study becomes relevant. And today, the only thing I want you to remember about star clusters is that we can determine their ages, and thus the ages of their stars, well, simply by plotting their colors and their brightnesses and examining the pattern that we see. So, the three rapidly spinning stars in the lower left part of this diagram represent measurements of cool star spin period in young open clusters. But beyond that, the only good information we have about the spin-age relationship for cool stars is from our own cool star, the Sun, at 4.6 billion years, leaving us with a 4 billion year gap. And that is where Kepler comes into the picture. See, the way we determine the spin period of a cool star is by measuring periodic changes in its brightness as dark spots on its surface cross its face and disappears on the backside again. That's illustrated by the star and the graph over on the left side here. Young stars spin really quickly, and they have large and big spots. So their brightness fluctuations are large and of short duration and relatively easy to measure. But as stars grow older, as you can see in the center and the right panel, they have fewer and smaller spots, and so the brightness fluctuations become smaller and of longer duration, and thus much harder to measure. And so, for clusters older than about 600 million years, we have not been able to measure the spin period for cool stars for decades. And so the construction of the cool star clock was on hold. But with Kepler, we've been able to break this deadlock because Kepler provided us with very precise measurements of the stellar brightness over years. And so, in 2011, the Kepler cluster study provided us with the first measurements of spin periods for cool stars in the 1 billion year old cluster NTC 6811. And today, I announce that we have now bridged this gap to the Sun by measuring the spin periods of cool stars in the 2.5 billion year old cluster NTC 6819. And these new measurements allow us to trace the spin history of our Sun from its current 26-day period to 18 days at about 2.5 billion years, to 11 days at 1 billion years, and so on. But we're not restricted to stars just like our Sun, because our measurements establish the spin-age relationship for stars that are both larger and more massive than the Sun, and stars that are smaller and less massive. So as you can see, we have made important progress in terms of measuring the spin history of cool stars. And by doing so, we have taken steps toward constructing this clock that will be able to provide us with their ages. So let me end by emphasizing the value of this clock to our study of planets and planetary systems beyond our own. As Lauren and Courtney will tell you in a few minutes, the field of extrasolar planets is branching into the studies of formation and evolution of planetary systems and of planets themselves and their atmospheres. And for all of these areas of study, knowing the ages of the planets is essential. Fortunately, a star and its planets form together at the same time, and so they share the same age. So if we can determine the age of a star, we also have the ages of its planets. And so as we find more and more rocky planets the size of Earth at distances from their stars so that life might have had a chance to evolve, an essential question becomes, how old are these planets? Because we know from studying our old planet that it went from being lifeless at 1 billion years through primitive life at 3 billion years to a planet teeming with complex intelligent life at 4.6 billion years. And we may have to learn interesting things about our own planet and the future of our own planet, the fate of our own planet, by studying solar-like, Earth-like planets around cool stars older than the Sun. So I just want to end by thanking my collaborators and the funding agencies supporting this work. Thank you.